Hello game developers, and welcome back to Let's Make Pong episode 2. Now last time we left off we had just finished implementing the basic skeleton of our Pong game. We have a window up and going, it's rendering nothing but it's rendering, and it's ready for us to start implementing our game. But before we do that I just want to talk a little bit about Pong itself. Kind of look at the gameplay elements and get an idea of what we're going to need to implement to make it happen. And so I have a screenshot here of Pong itself. You can see it's a very simple game, and if we kind of break it down you can see there's not that much to it, and it won't take that long to implement. The first thing you want to notice is we have a large playfield here. It's the entire screen for this game. And the field has a dividing line down the middle, just designating the area for player 1 and player 2. So we have a field, and we have 2 paddles. These can move up and down vertically along this one axis. They don't move horizontally at all. I think in the original Pong game they couldn't reach the very top or very bottom of the screen. That kind of gave room for the other player to shoot the ball down there and get it past them. So we may do that as well. Then we have the ball itself. It starts in the middle. Depending on whose turn it is to serve, it'll shoot towards the opposing player. So if player 1 is serving, it'll shoot out here towards player 2. It moves at a steady velocity until it hits a paddle, and then it gains a tiny bit of acceleration. So as the game progresses, the ball goes faster and faster. It just adds a bit of hecticness to the game and kind of gives it an inevitability to end eventually, which is what we want. We don't want people just sitting there batting the ball back and forth forever. And the ball can also bounce off the top and the bottom of the field itself. So if it comes down here this way, hits here, it'll bounce up this way while keeping its horizontal momentum. And then if it hits a side boundary, the left or the right, it'll score a point for the opposing player. So if the ball hits this boundary, player 1 will get a point. If the ball hits this boundary, player 2 will get a point. And then finally we have our score display. It just keeps track of the number of points a player has earned. As far as I know, you can go infinitely. The game doesn't actually end. There's no set score to aspire to. You just play until you've sufficiently destroyed your opponent. So, just to sum it up, the things we need to look at implementing will be a field, something to describe this rectangle and its boundaries. We'll need a paddle object so that we can set up 2 controllable paddles. We'll need a ball object so we can control its movement and its velocity. And we'll need to be able to keep track of and display the score for each player. So let's go ahead and look into that. Now the last time we left off I said we were going to look at splitting render into 2 separate methods, update and draw. The point of that is just for a bit of maintainability. We want to be able to keep the code as clean and as separated as possible. I mean, you could do all of your game logic and all of your rendering in this one method. Just do all your logic, and then once you're done with that, do all your rendering in the same method. But you don't really want a single method that's going to be a few hundred lines of code long. It's just a pain in the butt to try and work with. So we're going to split them up like this. We call update first, so we do all of our logic first. We make sure everything in the game happens, and then we draw what happened for that frame. So this is one frame. It'll come in here, it'll update, do all the logic for that one frame, and then it'll draw everything for that one frame, and then it'll go to the next. And speaking of going from frame to frame, we want to work with something called delta time. Let's go ahead and pull that in here real quick. We're going to do float dt. dt just stands for delta time. what delta time means. Delta is a change in quantity of something in mathematics, and so delta time is just a change in time, a change of time. It's actually the amount of time in seconds that has passed since the previous frame. So if you're running your game at 60 frames per second, that's going to be about 16 milliseconds, or 0.01666 repeating forever seconds. And that's how much time you have per frame to get everything done. Drawing everything, updating everything. Get it done in 16 milliseconds, and that'll keep you at 60 frames per second. So we shouldn't have any problem doing that. It seems like a very small amount of time, but you can actually fit a whole lot in there. So how do we get our delta time? Well, libgdx provides a method to do it for us by accessing the graphics class through the GDX static thing there. You see, we look at this. It's just provides a static interface for accessing the application stuff, graphics, audio, input, files, network stuff, and all your OpenGL things you can do directly here by clearing the screen, which we'll look at. So that's just a convenience thing. So we access graphics. We want to get delta time. There's actually two of them. There's get delta time, and there's get raw delta time. There's get delta time is smooth over several frames, so that gives you kind of a more consistent delta time to work with, whereas get raw delta time just gives you the flat number from the previous frame only, no smoothing involved. But we'll just use get delta time for now. And then our update and our draw methods are both going to use these, so we're going to pass that in. And we'll create these methods. Great, update, draw, there we go. Now, why do we want to use delta time? If you think about it, say you have just a simple, well, in our case, our ball is going to be moving across the screen. Say we want that to move 60 pixels per second, right? Or say we're just moving it 1 pixel per frame. That's a better example. So every frame, every time update here is called, we're going to add 1 to the X position of the ball, and that's going to move it 1 pixel to the right. Now we do that every frame, and say we're running at 60 frames per second, which is our target. That means that ball is going to move 60 pixels every second, which is our target. We want it to move 60. We want it to move 60 pixels per second, so that's great. But what happens if we take the same code and run it on a 10-year-old laptop, and it only manages to run at 30 frames per second? In our code, we just say, every frame, add 1 to this and move the ball. And so if it's only running 30 frames per second versus our 60 frames per second, the ball is only going to move 30 pixels in that same amount of time. And it goes the other way too. If you're running it on a super fast system, a system better than ours, and it manages to run the game at 120 frames per second, suddenly the ball is now moving twice as fast as we expected it to. And so to normalize things that are speed dependent, things that matter, it's called frame rate independence. We use the delta time to normalize that. Since we get the delta time as a fraction of a second, we just do all of our movement and all our calculations based on seconds. And so what we would do, instead of saying move X by 1 per frame, instead we're going to move X by 60 times dt. Right? So this won't actually be part of the code, but instead of doing X plus equals 1 per frame, we're going to instead do X plus equals 60, which is our movement. We want to move 60 pixels per second times dt. And so that'll wind up being some small amounts. Let's see. right? So it'll be 0.96. It'll wind up per frame, it's going to move 0.96 pixels. And then over the 60-second period, you know, it'll wind up close enough. So that's how we normalize that to work. So that's what we're using it for. And so we'll move on. So the first thing we want to define for our game is a field. Now we can do that in a couple of different ways. We can define the field. It's a rectangle, and our screen is already a rectangle. So if we wanted to, we could just use the screen boundaries itself as the field, which we'll probably do. We could also define the field as a smaller rectangle within the screen, and then we could draw the field and do fancy things with it, which we may do in the future. But I think for now we'll just define it as the boundaries of the screen. And to handle that, we're going to use the rectangle class that's provided by libgdx. Go ahead and import that, and we'll just call it field for now. Make it a new rectangle. We'll use that in a second. Now, what is a rectangle? It's just a class that is defined by an x and a y, and that's the top right corner of the rectangle. And then it has a width and a height. And using those, you can figure out the other three corners of the rectangle, right? So on your left side, you have x. Your right side of the rectangle is x plus width. The top side of the rectangle is y. And the bottom side of the rectangle is y plus height. And so using those, you can figure out the other corners, and that'll define a rectangle for us. And so what we're going to do in our create method, once the game is set up, we're going to go ahead and set the field rectangle that we just made to the boundaries of our screen. So we'll do 0, 0. And that's just saying that we want the top left of the rectangle to be up in the top left corner of the screen. And then we want the width and the height of the rectangle to be the width and height of our screen, which we defined earlier as 1280 by 720. So we'll just get that from the graphics device itself. We do it that way instead of just entering the numbers straight up. Like we could have just put 720 here instead of getting the height. But that way, if you go down here later and change this to something else, or if we decide to change this to something else, we won't have to change this either. Alright, so now we have a field, and we can use that later when we're doing collision detection with the ball to determine if it's hit a side of the ball. And that'll give us some future proofing, so that if we decide to make the field smaller than the screen at some point, all we'll have to do is change the size of the field here, and the rest of the code should still work. So we'll look at that later. So that takes care of the field, right? So that defines the field. It's going to be pretty much invisible. When we start rendering things, we'll look at rendering this dividing line just for visual sakes, but it doesn't actually perform any real gameplay, so we don't need to bother with it right now. We need paddles, we need a ball. Let's go ahead and look at the ball and the paddles actually. We'll probably do our first new class here, because the paddle and ball are both going to be game objects. They're going to be live things in the game that will be moving around, and they're going to share some common properties like a position, an X and Y position. They'll share a velocity since they move, and they'll share a width and a height since they'll have boundaries of their own that we can use for collision detection. So let's go ahead and make a new class that they can share. Let's just call it game object for now, if I can spell it correctly. And since we don't actually just want to make game objects, we're going to inherit game object to make our ball and our paddles. So we'll go ahead and make this abstract, meaning that this is just an outline of what a game object should be, but we can't actually make new instances of GameObject itself. Make a default constructor here. And then we want to think about what is going to be in a GameObject that both the paddle and the ball will share. The first main thing is going to be the position. And we can represent the position. There we go. We can represent the position of the ball as a vector, a 2D vector. Let's go ahead and call that position. So what is a vector? If you're not familiar with 2D vectors, definitely something you'll want to get familiar with as you progress in game development. Linear algebra is definitely something you want to get familiar with as far as math goes. Most of the times people use vectors as a static position in space. Like if you imagine those Cartesian grids you had to do in high school math, where you have an x-axis and a y-axis, and you have to plot them out from -10 to 10 on one axis and -10 to 10 on the other axis, and then your math teacher wants you to plot out 1, 2 here and 4, 5 here. That's pretty similar to what a vector is, except a vector is described mathematically as something that has both a magnitude and a direction. So if you think about it, trying to think of how best to demonstrate it, but if we just pull up Paint here, and say this is our fancy grid paper, right? And 0 is right here at the center. And say we have a little dot there. Let's make that use my paintbrush, make that bigger. Right around there. All right, let's say that's 2, 2. That's a vector 2, 2. That just means it has a direction, 2 across and 2 up, and the magnitude is actually the length of it from here back to its origin, back to 0. So that's technically what a vector is, but for the most part, until we get to the more complicated things, we can just think of vectors as positions in space. So we'll use a vector 2 to describe the position, since it'll hold both an x and a y component. And we'll also use a vector 2 to hold the velocity of our object. And the velocity is just going to be the change in space, or the change in position over time. So say our ball has a velocity of x equals 5 and a velocity of y equals 10. That means every frame it's going to want to move horizontally 5 and vertically 10. That's how its position is going to change. That's its velocity. So we can represent them that way. We can do some automatic getters and setters here, just to get those up and going. Do some automatic formatting there. And so that lets us get and set the velocity and the position. We can make some helper methods here just to make it a little bit easier to work with. So if we want to just get the x value, we can return position.x. If we want the y value, we return position.y. And if we want to get the velocity components, not sure if we'll actually use these or not, but I figure we'll go ahead and throw them in there for now since it doesn't take much time. Alright, so now we can access the position, the velocity, and the components of each one. So that's good. And the other thing we want to get in here is a boundary box, another rectangle for each one of them. That'll just define the area of space they take up in our field. So we're going to do a rectangle as well for those. We'll just call it bounds. And it's going to be just like our field, except the rectangle is going to be defined by the position of the object. So the top left corner will be the position of the object, and then the width and height will be different for the game object itself. We're going to want to pass in a width and a height to the object, so we can set that up in the bounds. And in our constructor, we'll just pass that over to the bounds so we can set it up that way. And then we'll set up a getter for that. Don't need to set up a setter since we won't be changing the bounds during the game, so we don't actually need to do that. There's that. And actually, in this get bounds, we're going to do this. We're going to update the bounds on the fly, because as the position changes, we want the boundary rectangle to change position as well to keep up with it. So what we'll do is set the x to the current position.x, and we'll set the y to position.y. Now every time we get the bounds rectangle using this method, it'll be current. It'll be exactly where the object is currently. So that's good. So that'll be automated for us. We won't have to check that and worry about that. Alright, so we have a game object that is defined by its boundary, its position, and its velocity. And we should be able to use that to implement our ball and our paddle. Let's do one more thing. Let's add a couple of more helper methods here, since we're going to want to move these around. Let's do a move method. This is just going to move the object to this position. So on our position vector, we're just going to use the set method and set it to x and y. And so this isn't a movement thing. It's not going to smoothly move it from one position to another. It's just going to move it directly to it. So you can use it. We'll use this to reset the ball and reset the paddles to like default positions if needed. And then let's also do a translate method. And as opposed to move, translate's actually going to move the object from its current position by the specified amounts, by its x and y position. So we will do position dot add, and these are just helper methods on the vector class itself, so we don't have to actually work with the components directly. And we do x and y, and so that's going to add our x and y to the position vector. So instead of moving it to a specific place, it's going to move it by that specified amount. So we'll use that to move the ball and the paddles around. And then let's also do, butchered that, let's do an update method. No, let's not do update. Let's do integrate. It's going to take our delta time. And integrating is just adding together our velocity and our position. So it's going to save us some extra typing from typing this out for each object itself. And all that's going to do is we're going to add the current velocity up here that we set elsewhere. We're going to add the velocity to the current position, and we're going to multiply the velocity by our delta time, like we talked about earlier. That's going to smooth out the movement across different frame rates. So to do that, we do position dot add velocity mul dt. So what's that do? Mul is a multiply helper method for the vectors, so it's going to multiply the velocity vector Need to think about that real quick, because that may not be right. Yeah, that's not what I want to do. Because if I use this, it's going to actually change the velocity vector by the delta time, and so that's going to butcher everything. So instead of doing that, let's do it by component. We'll do velocity x times dt and velocity y times dt. That way we won't change the velocity in case we need to work with it otherwise, but it will change the position, which is fine. So it's going to multiply the x component of the velocity by dt to smooth it out, the y velocity by dt to smooth it out, and then add those to the position. Alright, that should get us started. And we're at about 25 minutes now, so I think we'll stop here. And next episode, we'll look at implementing the ball, which is just going to inherit from this, and the paddles, which will inherit from this as well. It's going to be pretty simple. And we'll look at getting that set up, and then we'll probably work on rendering as well, so we can actually see something, see where we're at, and we'll take it from there. Thanks for joining me.